Hi, I'm Andy and this is question 7 on the AQA Decision 1 paper from June 2016. For more questions on this exam paper, click the eye in the top right corner. In question 7, a company operates a steam railway between 6 stations. The minimum cost in euros of travelling between pairs of stations is shown in the table below. And on figure 1, it asks us to use Prim's algorithm starting from P to find a minimum spanning tree connecting PQ, RST and U. It says, state clearly the order in which you select the vertices and draw your minimum spanning tree. So here is my table and I've got to start at P. So I'm going to put a 1 above here. The numbering along the top identifies which order I have selected the vertices in. So starting from P means we cross out the rest of row P. And looking down column P, we look for the shortest path from P to any of the other nodes. In this case, it's going to be T, which is 6. So the second vertex we add in will be at T. This means we cross out the rest of row T. And then we look down P and T and look for the next shortest arc. In column P, we've got a 7, but in column T, we've got a 5. So the shortest would be the 5, which is S. So we put a 3 above S, and we cross out the rest of row S. And then we look down columns 1, 2 and 3 to find the next shortest. In column P, we've got a 7. In column S, we can't beat that, and neither can we beat it in column T. So R is the next one we add in. So R gets a 4 above it, and we cross out the rest of row R. Looking down all 4 columns now, the best in column P is a 12. We can get an 8 in column R, and we can't beat that in the other ones, so we're going to go from R to Q. So Q gets a 5 above it. The rest of Q gets crossed out. And then all we need to do is find the shortest path that gets us to U. And in this case, we've got 2 choices. We could use QU or we could use TU. I'm going to use TU. Either way, the 5th vertex you add in will be vertex U. Now you don't have to actually write anything else down from this table in this question because you've identified the order of the vertices from the top. But just for completeness, you might write down that the order you selected them in was P, T, S, R, Q, U. Finally, don't forget to draw your minimum spanning tree because that's worth a mark. So we've got 6 vertices. So we've got P joined to R and T. We've got R joined to Q. We've got T joined to S and U. And that makes up our minimum spanning tree. In part B, we're told another station V is open and the minimum cost in euros of travelling to and from V to each of the other stations is added to the table in part A as shown in figure 2 part 1. So that's this figure here. And in part 1 of the question, we need to, by first removing V, obtain a lower bound for the minimum travelling cost of Aaron's tour. Notice that in figure 2 it's exactly the same table as before, just with an extra row and column for V added. So when it's asking us to find a lower bound by removing V, we essentially end up doing prims on exactly the same table as we did in part 1. So we may as well just use our answer here for this part. So the minimum spanning tree is going to be PT, which is 6, PR, which is 7, RQ, which is 8, TS, which is 5, and TU, which is 10. And if you add all of those together, you get 13, 21, 26, you get 36. Then we need to add our arcs in from V. But before I do this, let me just illustrate what's actually happening here. Let's say this is the minimum spanning tree we found, and we've also got some point V, which may be over here. And we need to make sure that that is connected as well. Imagine we are starting from V, we would have to go out of V, around the network somehow, and then back to V. Now, because it's a lower bound algorithm, it may not actually find us a solution to the problem. Maybe it will, maybe it won't. But looking at the table, the shortest 2 arcs from V are VU, which is 12, and either VR or VS, which are both 14. So I'll use VR. And the total there will give me 26. So that means that the lower bound is going to be 36 plus 26, which will give me 62. In B part 2, it says use the nearest neighbour algorithm twice, starting each time from V to find two different upper bounds for the minimum cost of orange tour. State with a reason which of your answers gives the better upper bound. So for this we're going to use figure 2 part 2. So they've actually been quite generous this year by giving you a table to work on for your nearest neighbour. Often you have to kind of do it in your head as you're going along. So starting from V, the nearest neighbour algorithm says go to the closest place that you haven't already been to each time. So starting from V, we can go to U. Okay, I'm going to write this down as I go along. And V to U is 12. And then from U, I look for the shortest place to go to. In this case, I could go to Q or T. That's why we're going to do it twice. So for this time around, I'm going to go to Q. And then the nearest place to go to from Q is R, which is 8. And then from R, the nearest place is P, which is 7. And then from P, the closest place is T, which is 6. From T, the only place I've got left to go to is S, which is 5. And finally, from S, you must make sure that you go back to the beginning. Lots of people lose marks, all of the marks for a question, if they don't go back to the start. So I've got to get back to V from S, and that is going to cost me 14. So adding all these together gives me 62. Next we'll do another path which will be similar. Starting from V, we're again going to go to U, which will be 12. But now instead of going to Q next, we're instead going to go to T. Then from T, the closest place is P. Then from P, the closest place other than T, which we can't have, is R, which is 7. Then from R, we're not allowed to go to P. We could go to Q, which is 8. And then we have to go to S next, which will be 10. And then finally, after S, we must get ourselves back to V, which is 14. And this time we get 67. So we've used the nearest neighbour algorithm twice, but we need to state with a reason which of our two answers give the better upper bound. Now remember, an upper bound is a possible solution to the problem, and the best solution out of two is going to be the one that has the least cost, in which case this one is the solution. So V, U, Q, R, P, T, S, V is better upper bound as it has a lower cost. By that I mean that 62 is less than 67. Finally, in part 3 it says hence find an optimal tour of the 7 stations, explain how you know this is optimal. So if we look at the upper bound here, it's 62, and if we look at the lower bound, it's 62. So in part 3 we can say that this tour must be the optimal tour because the lower bound is equal to the upper bound. Notice that part 2 and part 3 aren't asking the same thing. In part 2 it was just asking which is better out of these two, and then in part 3 we're saying that this is the best possible tour out of any tour because it's equal to the lower bound.